Before we get started taking our notes in section 5.1 about function composition, please make sure that you have printed the PowerPoint so that you have something to write as you record the notes going through this PowerPoint presentation. On your paper, it's much easier to read what we're talking about here with function composition. But our symbol for this is the little circle in between the G and the F. So we would say that we have G of F of X, which is the exact same thing as our notation G of F of X. And what it means is that we're taking the function f of x and we're putting it into the function g of x every place that we have the letter x in our function g. What we need to make sure, what this diagram is telling us, is that we're working with the letter x, that's our variable that's being defined. We're plugging the function f in every place that there was an x, from our function f, and then it's going into our function g, and when we make that transition, we will have come up with our composed function g of f of x that we denote like this. Okay, so in this slide we are going to take a look at composing various functions with the three functions at the top, the f of x, the g of x, and the h of x. And questions 1 through 7 are asking us to look at various combinations using those three functions. The first several involve two functions, and then the last two involve three functions. So those are going to be the most complicated of them all. If we look at our first function, we need to start with the f of x. That's the inside function. So f of x is going, we're replacing every letter x in the g function. So it's like g and then x squared minus 4x is getting plugged in every place that there's an x in my original g function. So let's see, I would have 2 minus square root of, no longer an x, I need to replace it with what's in my parentheses, x squared minus 4x, and then plus 3 is still under the parentheses. And I take a look at what I have there. I don't need to square anything, I don't have a fraction with a fraction, so this is as simplified as I can make it, and that is g of f of x. So now I can move on to the second question here, which is asking me to find f of g. So I'm going to start with that square root business from the g function, and so I'm taking, and I'm going to plug all that square root information into my f function, which has something squared and something minus 4 times what's in the parentheses. So I want to take all of this, 2 minus square root of x plus 3, that needs to be squared, minus 4 times 2, the square root. And unfortunately, when I look at this, I still have some work that I need to do. I need to square that first set of parentheses, I need to multiply by negative 4 to the second set of parentheses, and so all that simplifying means we still have some algebra to take care of. So if I square my first set of parentheses, I would get a 4 minus, normally I would just double the second term, but I also have a 2 there, so 2 times 2 gives me 4, and when I square the last one, I would remove my square root. And then when I look at multiplying by -4, I get -8, a positive 4 square root of x plus 3. So now I look and see if I have any like terms, and I have a number of like terms, but fortunately my square roots cancel out. I have a negative square root of -4 and a positive 4, so they're gone, and then no other x's, and 4 plus 3 is 7, minus 8 sounds like -1, so that big mess, f of g of x, actually turned out to be just x minus 1. Now, as I look ahead to some of the later problems, in particularly, I'm looking ahead to the ones that have 3, the triple compositions. I can see that in one of them, g of f is in there, and we did g of f in our first problem. But in the last one, I can see that h of g is in parentheses, and we haven't done anything with h in it yet. So I want to make sure that we handle h of g, because we haven't done anything with a fraction in it, and I don't really feel like doing all of these, to be perfectly honest. So let's make sure we take a look at h of g of x, and that means I'm going to start with the g function, and that has to go into my h function. So my h function has a fraction in it, and I need to plug in that gorgeous square root, 2 minus the square root of x plus 3. Every place that there was a x term in the original h function. So 2 times that's in my numerator, and then in the denominator I have so that's just beautiful. And if I do a little bit of simplifying, but I'm going to try to avoid doing too much simplifying, I need to distribute the 2 in the numerator, and so that would give me 4 minus 2 with the square root. And in the denominator, the 2 and the 1 can be added together. And I suspect you're going to tell me that, wait, we can't have a square root in the denominator, and you are perfectly correct. But using my vast knowledge of things to come, when you get into calculus, for whatever reason, you're allowed to leave square roots like this in the denominator. So I'm going to say that although your algebra skills are screaming at you saying that this is not simplified, I'm going to say it's okay to stop at this point. And we're done with our composite function. This is good enough. If you would like to take it further by multiplying by the conjugate, remember that's the one that needs 1 plus and 1 minus to multiply together, feel free. But I'm saying you don't have to. Now in the next slide I repeated these same questions, and I'd like to just use this space to talk about the triple composites, and we need to use some of our answers from this slide to get there. Okay, so on this slide I'd like to focus down on the second to last problem where we have h of, and then it tells us in parentheses g of f, and then of x. So we are going to pay attention to the parentheses here because that's giving us directions as to how we proceed. We need to go from the inside out on these compositions, that g of f needs to be done first and then second with the h of whatever we get from the g of f. We did g of f as the first problem, or the first composition in the last slide, so our result of that we know already as gorgeous answer. And again, I just copied that from the previous slide. If you feel like you really want to practice your function composition and do it again, go right ahead. Me, I copied it. But now I need to take this result and I need to plug this into the h function. So every place that there is an x in the h function, that gorgeous set of parentheses is going in. So let's see what happens when I plug all that into h. And I need a little more room here, so I would have 2 and then in the denominator and from our discussion in the last example that had square roots in the numerator and denominator, all I really want to do here is clean up a little bit of distributing and combining the numbers in the numerator and denominator. So I'm going to multiply by 2, and I would wind up with 4 and in the denominator I'm going to add the 1 and the 2. And this gives me the composition of h of the quantity g of f of x. So this is my final answer to that part. If I look at the last problem, this is telling me that I need to work on h of g. I need to find that one first, and then I need to use the f function. And so h of g we also found in the previous page, and so I copied that down. And again, it's gorgeous. So it is a fraction and now the question is, how am I going to take that and use it with the function f of x? Well, I'm going to take all of this and it's going into my f function. Every place that there's an x in my f function, no, sorry, I'm saying that wrong. My f function is going into this. So every place that there is an x, my f function is going into this beautiful fraction. So I would have and this big long fraction here looks awfully similar to the big long fraction that I got up in a previous problem, the one just above it. doesn't it? So if we look back on what we did in the first, say, 1, 2, 3, 4, 5, not that we did all 5 of them, but when we worked on the functions with 2, f of g or g of h or whatever those were, it's very important to pay attention which function goes into the other, because we don't get the same answer. G of f did not give us the same result as f of g. But when we got to 3 functions, whether we put in the parentheses g of f into h or f into the result of h of g, we got the same result. And that's because we could have done all of this by working from, in our functions, we worked from the inside out, but there's another process to be able to work from the outside in. For instance, in our first function, g of f, we started with the inside function f and went to g. We could have gone with our g function and plugged it into f. That's what I mean by going from the outside in. It's not how you were taught, but it works. And the last time I tried teaching this, no one wanted to hear about it, and everybody got confused, so I'm not going to show you how it works. But it is possible to proceed from the other direction, and that's why the 3 functions, we could go from the inside out or from the outside in. Either way, we get the same result. Now, we also may have noticed that the h of g of f is the same thing as the result of h of g of f. Notice the difference in the placement of parentheses. This is our associative property. It works for functions, and that's what I was talking about from the inside out or the outside in. The other one that I'd like to talk about is the identity function, so that if you take the identity function and compose it with the function, you will get the same thing as the function composed with the identity. And this is when you generate nothing but the letter x. So how do we find the identity function? Hold on to your horses. That's what's coming up next. Okay, so for these functions, we want to break down the function f of x into 2 separate functions. And so if we're looking at the f function here, I want to see if I can figure out what the inside function could be and what the outside function can be. So if I think of this as 2 separate pieces, what could be inside? What could be outside? So I kind of see that inside the parentheses, or under the square root, something's taking place, and then the square root is another function. So I might say that we would have to have the inside the function that under the square root has to be my inside function. And then f of x has to be outside the square root. So if I did this as f of g of x, I would be taking the x squared minus 4 and plugging it into my f function. And lo and behold, I would get what we started with. I'd like to apply the same thinking to the second equation we have here. And I can kind of see that the denominator here is an expression. So if I say that g of x, because that has to be going into whatever is taking place, and how would I be able to put that into a denominator? The only way that could happen if all I have is 2 over x. That's one possibility. What if you didn't like that one? What if you wanted to say that g of x was the square root, and f of x was 1 over x plus 1? That would also get you the same thing. So either of those would work to get you g of x. What we're doing here is called decomposing. We are breaking down the more complicated function into the two original f of x and g of x. And in the next slide, we're going to do this with 3 functions. So as I look at the f function again, this time I need to come up with something buried inside this function. So I have to break that down further. So I know that I need to have something minus 4 to be able to write this. That's got to be my starting place. So j of x has to be something minus 4. Well, if it's j of x, I need to call that x minus 4. Then I need to do something for my middle function to be able to replace my x's so that it then moves into the x squared minus 4. I don't want to change anything with the minus 4. That has to stay the same. So all I want to do is replace the x term with an x squared. So if I plug in x squared for my original x's, I would now have what's sitting underneath the cube root function, which means my f of x function has to be the cube root of x. And that should give me my original f of x function. For my g of x function, I have to think of breaking up the denominator in some way. So what would be the most basic way to write that denominator? I need 1 plus something, which again I call it 1 plus x. And then to actually take my 1 plus x and make it resemble what I have down there, I would replace my x with the square root of x. All that's going to do is change my j of x component to plug in the square root of x. And my f of x, I need to get a denominator in there. So I want to replace everything in the denominator with what I have from my previous 2 steps. And I think that'll give me what we want.